In Part 1 we covered the headline argument of this paper. Today we go deeper. We'll walk through the actual numbers behind each claim, the measurement theory the authors borrow to justify it, and then I'm going to do something the paper itself doesn't do. Rate it honestly, including where I think it falls short technically, and where I'd push the authors to go further. Fast recap for anyone joining fresh. The paper's authors, a team from the company Tessl, argue that a coding agent is not a model, it's what they call a system harness, a composite of the model, an agent scaffold, the environment, curated context, and feedback signals. Their claim is that changing any one of those non-model pieces can shift a benchmark score by a margin comparable to jumping an entire model generation. Yet nearly every leaderboard still reports one single end-to-end number for that whole 5-part system. Here's a piece of the paper's framework I skipped last time, because it's genuinely technical. They split feedback into 3 tiers by scope, latency, and trust. Inner loop signals, tests, types, lint, are fast, cheap, and narrow, scope to a single code change. Middle loop signals, reviewer agents, simulations, maintenance checks, capture taste and policy over many units of work. Outer loop signals, PR acceptance, revert rate, production incidents, are closest to ground truth but slow and confounded. Critically, they draw a line inside feedback. Verifiers are the strict subset, at return a binary pass or fail suitable for actually blocking a merge. Everything else informs but doesn't gate. This is the real terminal bench leaderboard, filtered to one fixed model, Claw Opus 4.6, across 6 different agent harnesses on the same task distribution. Same model, same tasks, and a spread of almost 22 percentage points, from 58 up to nearly 80. That gap is not noise. It's the harness, the scaffolding, the toolset, and the prompting strategy wrapped around an identical model. Worth understanding the lineage here, because it shows the field already sensing this problem and patching around the edges instead of addressing it head-on. The model-only family, human eval, MBPP, LevCode bench, correctly targets just the model component. The agentic family started with swe-bench, then iterated, verified, curated 500 human-validated tasks, multimodal added visual domains, and broadened the time horizon and is now OpenAI's own recommended replacement for verify. swe-bench went the other direction entirely, trading human validation for raw scale, over 32,000 tasks across 20 languages. Terminal bench broadened further into general command line tasks, and has become the de facto standard everyone quotes. Every one of these iterations improved something. None of them touched the structural problem this paper raises, because they all still collapse the whole system harness into a single end-to-end number. The paper doesn't rest on one table. Practitioner reports show 4 to 10 point swings for Claude Opus 4.5 between standardized and custom scaffolds on swe-bench verified. The OpenHands harness reaches 77.6% with models that score several points lower under a standardized mini-agent harness. A separate study, swe-bench, found that holding the scaffold fixed and only swapping the base model moves the resolve rate 2 to 3 times over. And AI-21, analyzing over 200,000 swe-bench runs, found that orchestration choices, container allocation, and even the evaluation random seed measurably move the pass rate at a fixed model and fixed harness. This is infrastructure noise being mistaken for model capability. Now the technical case against single reference grading. swe-bench plus found solution leakage inside the issue text itself in almost a third of tasks, and nearly a third of passes came under insufficient test coverage. A differential testing study went further, finding that 7.8% of officially resolved patches actually fail the original developer's own tests, and 29.6% diverge from the reference patch's runtime behavior entirely, despite being marked correct. Separately, the AI Dev dataset measured 456,000 real agent authored pull requests across 61,000 repositories and found real-world acceptance rates of just 35 to 64%, well under the 70% plus headline figures benchmarks report. The third symptom gets genuinely interesting once you look at their own reference system, in S2. Some harness components exist purely to evaluate other components. Mutation testing doesn't test the code, it tests whether the unit test suite would actually catch a bug if one were introduced. An agentic reviewer grades the quality of the lint rules the coding agent itself wrote and maintains. You end up with a stack of verifiers checking other verifiers, several layers deep, and a single end-to-end pass or fail number flattens all of that structure into one bit of information. So, has anyone actually tried component-level evaluation? A little in adjacent work the paper cites. Peak scores in agents along context orientation and in context learning directly, instead of end-to-end task completion. Decision Bench evaluates how well an agent delegates subtasks across a pool of models. Skills Bench isolates the lift you get from a single agent skill, holding everything else constant. And meta-harness goes furthest, treating the entire harness as something you can search over and optimize automatically. The honest caveat the paper itself makes: none of these four were built specifically for coding. They illustrate the shape of the solution without yet being the solution. Here's the academic backbone holding the argument together, borrowed from social science measurement theory. You separate the construct, what you actually care about, like the bug is genuinely fixed, from the operationalization, how you actually measure it, like a hidden test passing. Single reference hankering is framed as a content validity failure. The test set doesn't cover the full space of what solving the bug could mean. Conflating model and harness into one score is framed as a discriminant validity failure. The measurement instrument literally cannot tell two different things apart, and reports one number as if it could. They're concrete asks. First, leaderboards should require full metadata at submission: model, harness version, environment hash, dataset version, and at least one ablation across a non-model axis. Second, move from single reference test sets to behavioral verifiers and accept multiple valid solution shapes, closer to property-based testing than exact match grading. Third, evaluate individual harness components in isolation, the same logic that splits unit tests from integration tests and ordinary software engineering. Credit where due. The paper doesn't just present its argument and walk away, it directly engages three objections a skeptical reviewer would raise. To end-to-end scores reflecting real usage, they agree, but argue that's a case for adding component signal alongside it, not replacing end-to-end scoring, the same resolution software engineering reached with unit versus integration tests. To decomposed evaluation being too costly, they argue the real cost today is misattributing improvements and picking the wrong system based on a misleading signal, and that even one partial component metric added to an existing score already helps. To the reference solution being a reasonable gold standard, they concede the point. Conditionally, it's reasonable only when a task is specified tightly enough that the reference is genuinely the only sane shape, which they argue is the exception in real engineering work, not the rule. Now let me actually criticize this, because a paper this well argued still has real gaps. It's a position paper. There is no new benchmark, no experiment showing their own three remedies actually work in practice. Some of the supporting evidence comes from Tessl's own company blog and their own product, an S2, which is a legitimate conflict of interest to flag even if the underlying observations are sound. The component-level evaluation proposal doesn't solve the hard problem, it just relocates it. If you score 5 components separately, you still need to decide how to combine 5 numbers into one decision, which is the exact aggregation problem they criticize end-to-end scores for. Table 1's 22-point spread is compelling, but the paper doesn't cleanly separate genuine harness design quality from differing token budgets, retry limits, or tool call ceilings between harnesses, even though their own cited AI21 study shows that kind of infrastructure noise is real. And when they propose LLM as judge review as middle-loop feedback, they never examine the reliability of that judge itself. The same discriminant validity problem they raise for benchmarks could apply to their own proposed fix. Finally, this is submitted to a co-located workshop, not a full peer-reviewed venue, so it hasn't yet faced the level of scrutiny a flagship conference paper would. A few more technical gaps for anyone thinking about extending this work. The paper shows variance exists, but never runs a formal variance decomposition, an ANOVA-style analysis that would let you say precisely what fraction of total score variance is attributable to the model versus the harness versus infrastructure noise. Second, they propose grading design-level quality, sound abstractions, architectural fit, but never validate that these invariants actually correlate with what a real human reviewer would approve, which is exactly the kind of construct validity check the paper demands of everyone else. Third, with 3 feedback tiers running simultaneously, they never specify a resolution protocol for when tiers disagree. What happens when inner loop tests pass cleanly but the change gets reverted in production 2 weeks later? And finally, behavioral invariant does a lot of load-bearing work in this paper's argument, but it's never given a precise, checkable definition. It stays at the level of a good idea rather than a specification. So, 3 separate scores, because innovation, argument quality, and future potential are genuinely different questions. First, argument quality. 8.5 out of 10. The central claim is precise. It's backed by real data from multiple independent research groups, not just the author's own numbers, and it's grounded in legitimate measurement theory rather than vibes. It loses points for the self-citation pattern and for offering zero new empirical validation of its own proposed fixes. Second, innovation. I'd put this at 7 out of 10. To be clear about what that means, the paper doesn't invent a new technique. What it does well is take knowledge that was already scattered across practitioner blog posts, conference talks, and half a dozen independent papers, and formalize it into one citable, precise vocabulary: system harness, agent harness, inner middle outer loop, verifiers versus feedback. That's genuinely valuable synthesis work, and the verifiers of verifiers framing is sharper than anything I'd seen elsewhere. But the core critique itself traces directly back to the benchmark lottery paper from 2021, and this is explicitly a position paper, not a new algorithm, dataset, or method. Third, and this is the one I'm most excited about, future research potential. 9 out of 10. This paper is a better map of open problems than it is a finished solution, and that's exactly what makes it valuable as a citation anchor. Component-level benchmarking for agentic coding barely exists yet. Meta-evaluation of LLM as judge verifiers barely exists yet. Compute-normalized harness comparison barely exists yet. Every one of those is a legitimate, fundable research direction that this paper hands you on a plate, clearly scoped and clearly motivated. If I were reviewing this for the next version, here's what I'd ask for. 1. Ship an actual reference component-level benchmark, even a small one, not just the proposal for one. 2. Rerun something like Table 1 at matched compute budgets across harnesses, so the 22-point spread can be attributed to design rather than spend. 3. Formalize behavioral invariant using existing, precise vocabulary from property-based testing and design by contract, instead of leaving it as an intuitive term. 4. If you're proposing LLM as judge review as middle loop feedback, report its iterator reliability against human reviewers. And 5. Seek independent replication of the NS2 findings outside Tessl to take the conflict of interest question off the table entirely. Before we wrap, what does this actually mean if you're building or buying agentic coding tools right now, not writing papers about them? First, treat any bare leaderboard percentage as underspecified. Ask what harness, what environment, what seed produced it, because the AI dev data shows real-world PR acceptance running 35 to 64% even when headline benchmark numbers clear 70. Second, don't wait for the field to standardize. Build your own small component-level smoke tests today. Even 3 or 4 targeted checks beat one opaque end-to-end pass rate. Third, log your inner, middle, and outer loop feedback separately from day one, because retrofitting that separation after a failure happens is exactly the expensive, intuition-guided ablation this paper warns about. That's the deep technical pass. Strong argument, real data, genuinely exciting research directions, and a handful of gaps I'd love to see closed in a follow-up. If you're working on agentic coding evaluation, this paper and its reference list are a serious reading list on their own. Links in the description. See you in the next one.